Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science, Commerce and Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Students, today we are going to study the topic which is called as Forward and Reverse Bias Characteristics of PN Junction Diode and Diode as Active Component. So today we are going to study only forward characteristics. In the next lecture, we'll cover reverse characteristics because the topic is lengthy. So the title is Forward and Reverse Bias Characteristics, that is also called IV characteristics of PN junction diode and diode as active component. Why PN junction diode is called as active component, that also we are going to study. So this is fifth lecture almost. In previous lecture, we have understood that in forward bias condition, the width of depletion layer decreases. In previous lecture, we have already understood that in forward bias condition, the width of depletion layer inside PN junction diode decreases, and in reverse bias condition, the width of depletion layer increases. So how does the depletion layer is created? And because of creation of depletion layer only, there is creation of barrier potential as well as junction capacitor that you have understood, and you are requested to watch the videos again and again previous so that you will clear your concepts. We also studied the measurement of voltage across the diode in conducting and non-conducting condition. So I have given the focus in the previous lecture on measurement of voltage across the diode in conducting condition, means in forward bias condition. And when diode conducts, diode conducts after 0.7 volt of an applied input voltage, because the barrier potential magnitude is in reverse direction to the applied forward voltage, and it is zero point 0.7. Therefore applied input voltage must be greater than 0.7 volt, then only diode conducts. And we have already measured or studied how to measure the voltage across conducting diode and non-conducting diode. And we have came to conclusion last time only that whenever PN junction diode starts conducting, of course after 0.7 volt, the measured voltage across PN junction diode is always 0.7 volt, and the voltage above the 0.7 volt of applied input voltage becomes short circuit because diode started conducting. And this is the last conclusion. Now let us start today. Now we will study IV characteristics, current I versus voltage V, that is IV characteristics of PN junction diode in forward bias condition. So in forward bias condition today we'll focus to study the forward bias characteristics of PN junction diode. Anode of the diode should be connected to the variable voltage source as shown below. And anode of the diode is connected to the variable voltage source. Variable means what? Input voltage applied is not constant. 5 volt, 2 volt, 3 volt. That input voltage is varying. Its magnitude is changing, and will apply variable voltage input voltage to the anode of the diode. But remember that variable input voltage is applied such that anode of the diode is connected to the positive of variable battery, and cathode of the diode is connected to the negative of variable battery. That will understand in the diagram. So here this is the diagram for circuit diagram for forward bias. FB means forward bias characteristics of PN junction diode. So where is the diode? Here is the diode D. So this is the diode D, and as you are aware that we always measured the voltage across diode by connecting the voltmeter across the diode, means in parallel to the diode. So this voltmeter is measuring VD, means voltage across the diode. You remember we always connect the voltmeter such that positive of voltmeter is to the anode of the diode, you see here, and negative of the voltmeter is to the cathode of the diode. Now what we have done here in this diagram, this is the input voltage V in, which is having magnitude 10 volt. Input voltage V in is having magnitude 10 volt, of course DC voltage 10 volt battery. And then we have taken one variable resistor, and variable resistor is having three terminals. So upper terminal of variable resistor is connected to positive of battery. Lower terminal of variable resistor is connected to negative of battery, and variable terminal of the variable resistor, which is called wiper also. Variable terminal of the variable resistor is connected through current meter, to the anode of the diode, and variable terminal of variable resistor is connected to the anode of the diode through the current meter, and this current meter milliampere is in series with the diode. Therefore, whatever current is flowing through the diode, it is measured by this current meter. And now, when you change the wiper or variable terminal of this variable resistor, the voltage at this point is changed, and that's why it is said variable voltage source. So this variable resistor along with battery, this battery, this entire circuit, which having only two component, battery fixed volt and variable resistor as a second component, is called variable voltage source. And now here, this is VR, means variable voltage. R here we have not taken for a resistor. So here variable voltage, it is understood like that, voltage across resistor which is varying, variable voltage. So VR. So VR is the variable voltage, and here upper terminal is plus and my lower terminal is minus of this voltmeter, which is connected to the variable terminal of the variable resistor. And here this terminal, when you change in upward or downward direction, this voltage changes. The voltage will change from 0 volt to 10 volt. Voltage will change from 0 volt to 10 volt because our input is, our maximum is 10 volt. And now here we'll vary this wiper of the variable resistor, which is also called as variable terminal of variable resistor, and we'll measure this voltage, and we'll measure the current, as well as we will measure the voltage across diode, So three parameters we are going to measure in this circuit diagram. Voltage which we are varying, that is variable voltage, and because of these changes in the voltage, that is variable voltage, how much amount of current is flowing through the diode, that we are measuring, that is called diode current ID. And we are also measuring the voltage across diode. So there will be three columns, and that we are going to study in the next slide. But here let me explain you that when this voltage VR is less than 0.7 volt, when this voltage VR is less than 0.7 volt, all of you know that PN junction diode will not conduct. PN junction diode will not conduct, and it will behave as open switch. Secondly, all of you know that internal resistance of voltmeter is infinite, because voltmeter should not short circuit the battery. And exactly opposite, if the internal resistance of voltmeter is infinite, means maximum, then current meter, when you talk about a current meter, internal resistance of current meter should be very low, and if it is ideal, it should be zero. So this current meter milliamperes, internal resistance is zero, means neutrally you can short this positive terminal and negative terminal. You can consider it is a short circuited, but very few ohm resistance is offered by any current meter, and by any voltmeter resistance is very high in mega ohm, very high in mega ohm. So in this way here, when you change this voltage, then what will happen, because of the internal resistance of this current meter which is very less, this voltage gets applied to the anode of the diode. This variable voltage gets applied to the anode of the diode, and already the cathode of the diode is connected to the negative of the battery through the resistor RL, that is a load resistor, through the resistor RL, that is a load resistor. So this is a circuit diagram in which we are using the RL. Even though if you don't use the RL, there is no problem, but RL is always used here so that we can control the current flowing through the ID. Current flowing through the ID means diode. So here, when input voltage is suppose 0.1 volt, input voltage is suppose 0.1 volt, that is VR, then this 0.1 volt will get applied to the anode of the diode. And you know that 0.1 volt is not sufficient voltage to forward bias the PN junction diode. Therefore, PN junction diode will remain as non-conducting device, means it will behave as open switch, and therefore the voltage measured across PN junction diode will also be zero point 0.1 volt because it is open switch. And this concept we have studied in the previous lectures. And in this way, if variable voltage is increased from zero point 0.1 volt to zero point 0.2 volt, zero point 0.3 volt, zero point 0.4 volt till zero point 0.7 volt, the diode is not conducting at all. Therefore, till zero point 0.7 volt, the voltage across VD, means across the diode, will be zero point 0.1 volt, zero point 0.2 volt, zero point 0.3 volt, zero point 0.4, zero point 0.5, zero point 0.6, and zero point 0.7. So, because we have considered this will not conduct at all till zero point 0.7, and therefore up to zero point 0.7 volt, if this diode is not conducting, it is behaving as an open switch, and voltage measured across this diode, that is VD, is as good as equal to voltage applied to this diode. But what about current? As we said that diode will not conduct at all up to zero point 0.7 volt, means current flowing is zero. Current flowing is zero, and therefore in the next graph, next slide, you will understand that applied voltage VR 0.1 volt, current flowing through the diode 0, and measured voltage across diode is again zero point 0.1 volt because it is behaving as open switch. And same thing will happen for all applied voltages VR 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and zero point 0.7. Current will be 0, but VD will be same. But real fact is what? After zero point 0.7 volt, after zero point 0.7 volt, when diode starts conducting, what will happen about the VD? And that already we have cleared in the previous lecture. If applied input voltage to the diode, that is VR in our case, is 1 volt, is what? 1 volt. Then that 1 volt is greater than zero point 0.7 volt, which is the minimum voltage required. Zero point 0.7 volt is the minimum voltage required to force the diode into conduction. Therefore, at once the diode starts conducting, the voltage across the diode is always zero point 0.7 volt, and current will start flowing, but voltage measured across diode is zero point 0.7 volt only, even though you have applied VR as 1 volt. Even though you have applied VR as a 1 volt, then again the same question comes, what will happen, or where is the zero point 0.3 volt, which is over and above the zero point 0.7 volt? So the answer you know very well. The zero point 0.3 volt above the what 0.7 volt is short circuited by conducting diode, and another language it is said the zero point 0.3 volt above the zero point 0.7 volt, because applied voltage is 1 volt. So voltage above the zero point 0.7 volt is zero point 0.3 volt, and that zero point 0.3 volt is dropped across PN junction diode. So this is very simple thing. But here let me tell you one more thing here. This PN junction diode is exposed to the room temperature now, because we are conducting the practical at room temperature, and room temperature is 27-28 degrees centigrade. Therefore, when you perform the practical at room temperature, instead of conducting at zero point 0.7 volt, this diode starts conducting at zero point 0.6 volt only. At zero point 0.6 volt only means little bit early to the zero point 0.7 volt, because diode is a semiconductor component, and if you expose it to the high temperature, then the electrons in the PN junction diode are thermally excited, and therefore that PN junction diode will start conducting at zero point 0.6 volt only instead of zero point 0.7 volt. And this is entire, you can say that, understanding of this particular diagram, and whatever I have explained you here, that I am going to read in the next slides, and again we'll try to understand here each and every block in this diagram. So the diagram is very simple. There are two voltage measured. One is the voltage across diode, and second is the voltage applied to the diode, that is variable resistors voltage. And third parameter which is measured is called current flowing through the diode, because we wanted to see that when does the current starts flowing through the diode. we know that the diode will start conducting after zero point 0.7 volt, after zero point 0.7 volt ideally, but practically it will start conducting at zero point 0.6 volt onwards only because of room temperature. And let us proceed for that now. So look at the diagram again. So here, forward bias characteristics of PN junction diode, that is also called IV characteristics, current versus voltage. And always on y-axis the current is taken and on x-axis the voltage is taken. Current versus voltage characteristics. And this is for practical diode. This is for practical diode. So let us look at the diagram and you will understand from the diagram very well or very clear that the x-axis is here. On x-axis we are applying voltage in positive direction, that is plus Vd. Means here we are, when we plotting the graph, we are plotting the graph of voltage across diode Vd versus current flowing through the diode. Sorry, current flowing through the diode versus voltage applied to the diode. So here Id and Vd. So current flowing through the diode is taken on y-axis, voltage across the diode is taken on x-axis. Here we are not plotting the graph of voltage applied to the diode, that is VR, and current flowing through the diode. We are plotting the graph of voltage across the diode, voltage across the diode, not applied to the diode, and current flowing through the diode. So look at the diagram very carefully. The graph is in first quadrant because applied voltage is positive and current is also positive. So here both parameters are positive, so graph is in first quadrant. So here up to 0.6 volt, up to 0.6 volt, zero current flows here. On y-axis current is there, so no current is shown on y-axis up to 0.6 volt. After zero point 0.6 volt, slightly the current starts flowing. See here, after zero point 0.6 volt, slightly current starts flowing, and when you apply the voltage 0.7 volt or greater than 0.7 volt, when you apply the voltage 0.7 volt or greater than 0.7 volt, the current will go on increasing. See here, current will go on increasing, but the voltage across diode remains 0.7 volt only. But the voltage across diode remains 0.7 volt only. Here on y-axis, the current is there. So you can see the current goes on increasing. But if I just put here Vd, because on x-axis there is what? Vd means voltage across diode. So if I mark here as a Vd, then you'll observe that Vd is 0.7 volt only. And this is the IV characteristics of practical diode. Here we have written 0.7 volt for silicon and zero point 0.3 volt for germanium. So if you plot for germanium, here at zero point 0.3 volt only or below than that only the diode will start conducting. But now widely used is silicon. So this graph is very simple. Why it is in first quadrant? Because both are positive. Voltage across diode Vd and current flowing through the diode. Because we are studying the characteristics of forward bias. We are studying the characteristics of forward bias. So now let us go to the next slide. As shown above, when variable voltage VR is applied, as shown above means not this diagram, as shown in the circuit diagram of this here. See, when variable voltage VR, as shown above, as I told you, this battery of fixed voltage and variable resistor combining together is converted into a variable voltage source, and when you change the wiper or variable resistor of this variable terminal, the voltage at this terminal can be changed, and that is called variable voltage. So here you can change this voltage from zero point 0.1 volt to 10 volt, 0.1 volt to 10 volt. So this diagram's explanation is given over here. As shown in above diagram, when the variable voltage VR is applied at the anode of the diode starting from zero point 0.1 volt to 10 volt, starting from zero point 0.1 volt to 10 volt, at that time diode does not conduct up to zero point 0.6 volt. This is important. At that time diode does not conduct up to 0.6 volt, and the current starts flowing through the diode is and current flowing through the diode is 0 up to zero point 0.6 volt. So that is what we have explained you here. Our PN junction diode, we are applying here this variable voltage, from zero point 0.1 volt to 10 volt, zero point 0.1 volt to 10 volt. But our diode will not conduct up to 0.6 volt, up to 0.6 volt, ideally 0.7 volt. our diode will not conduct up to 0.6 volt, and therefore current flowing through the diode up to 0.6 volt is 0. But above zero point 0.6 volt, when you apply this variable voltage, then current starts flowing through the diode, but the voltage across the diode is zero point 0.7 volt only for all applied voltages 1 volt, 2 volt, 3 volt, 4 volt, like that. But the current goes on increasing, and that is what here in this paragraph it is mentioned. As shown above, when the variable voltage VR is applied to the PN junction diode at the anode of the diode starting from zero point 0.1 volt to 10 volt, at that time diode does not conduct up to 0.6 volt, up to 0.6 volt, and the current start flowing through the diode is 0, or current flowing through the diode is 0 up to 0.6 volt. So till 0.6 volt diode does not conduct. But our variable voltage is from zero point 0.1 volt to 10 volt. Now let us see next slide what happens after zero point 0.6 volt. But after zero point 0.6 volt, the current starts flowing. But after zero point 0.6 volt, the current starts flowing, and it increases, as applied voltage increases. And it increases as applied voltage increases. The voltage across the diode, that is VD, remains 0.7 volt only for all applied input voltages from 1 volt to 10 volt as shown in IV characteristics. From 1 volt to 10 volt it is. From 1 volt to 10 volt as shown in IV characteristics. So here from 1 volt to 10 volt, after 1 volt, you can say roughly the applied voltage is 1 volt to the diode VR, but voltage measured across diode remains as how much volt? 0.7 volt only as shown in IV characteristics. So what are the IV characteristics here? See this. The voltage across diode is always 0.7 volt only. Current goes on increasing. Current goes on increasing. So in this way here, that parameter is very important. Now, as I told you that here, the diode conducts from zero point 0.6 volt instead of zero point 0.7 volt. The diode conducts from 0.6 volt instead of 0.7 volt because the diode is at room temperature and diode is a semiconductor component. Therefore, the conductivity of the diode is increased due to room temperature. Therefore, the conductivity of the diode is increased due to room temperature, and therefore in this IV characteristics, we have shown the current starts flowing from 0.6 volt only instead of zero point 0.7, exactly at 0.7, not just from zero point 0.6 only, because it is a practical IV characteristics, and ideal also we are going to study. So that is what here written. The diode conducts from zero point 0.6 volt instead of zero point 0.7 volt because the diode is at room temperature and the diode is a semiconductor component. Therefore, the conductivity of diode is increased due to room temperature. The electrons in diode are thermally excited at room temperature and current starts flowing zero point 0.6 volt instead of 0.7 volt. So this is the support for this semiconductor. Thermally excitation of the electron takes place at room temperature. So here the IV characteristics, when we take the reading, you are again going to perform the same practical forward bias and reverse bias in lab, and you are going to take the readings like this. The graph is in the first quadrant because voltage and current are positive. Now here we have taken that voltage applied, that is VR. Voltage applied, that is VR. Voltage across diode and current flowing through the diode. So note up to this point, when you apply the voltage VR to the diode 0.1 volt, the voltage across diode is again 0.1 volt because diode is open switch, and voltage across open switch is the voltage whatever you apply, that we have studied in previous lecture. Therefore, from zero point 0.1 volt to 0.7 volt, you see the applied voltage VR with the help of variable resistor. The applied voltage VR with the help of variable resistor is 0.1 to 0.7 volt, and voltage measured across diode is again 0.1 volt to 0.7 volt. So these first two columns, first column and second column. But remember, current flowing through the diode till 0.6 volt, was 0. Current flowing through the diode till 0.6 volt was zero, and exactly at zero point 0.6 volt, a small amount of current, let's say 0.5 milliampere, not even 1 milliampere, exactly at zero point 0.6 volt, a small amount of current, say zero point 0.5 milliampere, starts flowing through the diode. At zero point 0.7 volt, little bit more amount of current flows. At zero point 0.7 volt, little bit more amount of current flows. And after zero point 0.7 volt, you see the current goes on increasing, but voltage across diodes here, red mark it is given here. Even though if you apply 0.8 volt, 9.9 volt, 1 volt, 2 volt, the applied voltage to the diode now after 0.7 volt is greater than its barrier potential. Therefore, diode started conducting, and voltage above zero point 0.7 volt of applied input voltage gets short circuited, and measured voltage across diode is zero point 0.7 volt only. And therefore, we have taken into consideration from zero point 0.1 volt only, you can say, sorry, from 1 volt you can say 1 volt to 10 volt. So 1 volt, 2 volt, 4 volt, 8 volt, 10 volt. So here all these voltages across the diode are zero point 0.7 volt only. And therefore in the diagram you see here IV characteristics, this voltage is zero point 0.7 volt only. Voltage across diode is zero point 0.7, straight vertical line. Therefore, after the diode starts conducting, means after zero point 0.8 volt, the voltage measured across diode is zero point 0.7 volt only, and these are the IV characteristics. So in above table it is observed that the voltage across diode, that is VD, remains zero point 0.7 volt at zero point 0.7 volt only, but the current ID goes on increasing when applied voltage VR increases. So this is a very simple forward bias characteristics. The forward resistance of diode goes on decreasing. Now when you force the diode into conduction, when you force the diode into conduction, diode will start conducting, and you applied the voltages to the diode starting from zero point 0.1 volt to 10 volt, zero point 0.1 volt to 10 volt. At 10 volt you see the current is very large, 11 milliampere. At 10 volt the current is very large at 11 milliampere. And in this way here, when you apply more and more voltage to the diode, the forward resistance of diode goes on decreasing when applied voltage increases, because the diode is semiconductor component. Because the diode is a semiconductor component, therefore forward resistance of the diode decreases. Therefore the forward resistance of the diode decreases as diode is a semiconductor component. In case of an ideal diode, the diode current ID, in case of an ideal diode, the diode current ID will start flowing only after zero point 0.7 volt of applied input voltage VR, as shown below. So in case of ideal diode, see here, now these are the forward bias characteristics of PN junction diode into bracket ideal, into bracket ideal. So in ideal case, what will happen, see here, up to 0.7 volt, up to 0.7 volt, the current is zero. No current is shown here up to 0.7 volt. And after 0.7 volt only the current starts flowing. So here see, here I have marked the arrow, here I have marked the arrow, and it is shown 0.7 volt only. So this is a vertical line. Exactly at 0.7 volt current starts flowing, and current goes on increasing because on y-axis there is a current. Current goes on increasing after 0.7 volt, of course, applied voltage, then 1 volt, 2 volt, 3 volt, 4 volt, then up to 10 volt. The current increases, but voltage across diode is 0.7 volt only. So this is ideal. But practically what happens? Practically from zero point 0.6 volt only the current starts flowing, as shown in the practical diagram. So here in the practical diagram you can immediately notice from zero point 0.6 volt only the current started flowing. And in ideal case from 0.7 volt only. That is what here ideal characteristics of PN junction diode. And ideal thing is imaginary. It is not possible in real life or real world. So this is a practical. So here, sometimes here, sometimes the practical graph is also as shown below. So what is the difference in this graph and in that graph is here. Here is the current, forward current flowing through the diode milliampere, forward voltage across the diode. So here you see the current started flowing at zero point 0.6 volt only. So this part is same. But here you can note that this line is little bit extended on the right hand side, little bit extended or inclined on the right hand side. This is not a vertical. This is not a vertical exactly. And this is what sometime the characteristics are also like this. So voltage across diode slightly increases. Voltage across diode slightly increases. And here again there is one more diagram. So here see 0.6 volt onwards only the current started flowing. But but actually ideally current will flow from zero point 0.7 volt only, but practically zero point 0.6 volt onwards current started flowing, and this line is again little bit inclined on the right hand side, little bit inclined on the right hand side, not a vertical exact, not a vertical exact. So sometimes this type of the characteristics are also observed. And now from this we'll understand that, so very simple concept. Whenever a PN junction diode is forward biased by connecting the anode to the positive of the battery and cathode to the negative of battery, that is input voltage, diode is shown as good as conducting device. Diode is shown as good as conducting device. Of course, this is greater than zero point 0.7 volt. Therefore, it is replaced by a closed switch. Therefore, it is replaced by a closed switch. But remember, it is not a perfect closed switch because resistance between anode and cathode are AC. Resistance between anode and cathode are AC of diode is in few ohm. It is in few ohm, whereas for closed switch the resistance is zero. So it is considered like that, only considered. As shown in above, the forward bias PN junction diode offers very low resistance. As shown above, the forward bias PN junction diode offers very low resistance in few ohm. In few ohm. Therefore, it is shown as good as closed switch. Therefore, it is shown as good as closed switch, not a perfect closed switch it is, but most of the time we consider in electronics the forward bias condition when you use the diode and when you apply the voltage greater than zero point 0.7 volt, greater than zero point 0.7 volt, it starts conducting, means behaving as a closed switch device. But again remember, for 1 volt also it is closed switch, for 2 volt also closed switch, for 3 volt also closed switch. But at 1 volt there is a resistance, at 2 volt there is a resistance, at 3 volt there is a resistance, and this forward resistance goes on decreasing as applied voltage increases because diode is a semiconductor component. Therefore, this is consideration only. The forward resistance of PN junction diode decreases as forward applied voltage increases. The forward resistance of PN junction diode decreases as forward applied voltage increases because PN junction diode is a semiconductor component. Because PN junction diode is a semiconductor component. The resistance of all semiconductor devices. The resistance of all semiconductor devices decreases when either applied voltage is increased or temperature surrounding to semiconductor device or component is increased, and therefore it is said that all semiconductor components are having, or semiconductor material is having, negative temperature coefficient. All semiconductor component or semiconductor materials are having negative temperature coefficient. So this paragraph you read it again, you will understand very simple it is. Now here, in case of metals, the resistance of metal increases with, in case of metals, the resistance of metal increases when either applied voltage is increased, when either applied voltage is increased, but into bracket it is here very carefully, that is when current is excess. So in metal, when you pass more current than its capacity, in metal, when you pass the more current than its capacity, metal will start heating, whatever metal it is, copper, aluminum, gold. So when you pass the more current than its capacity, metal will start heating. And here you see, in case of metals, the resistance of metal increases when either applied voltage is increased, into bracket, when current is excess, or temperature surrounding to metal is increased, or temperature surrounding to metal is increased. If you heat the metal and if you pass the current through the metal, then because of the heat, the temperature, because of the heat, that is temperature, the resistance of metal increases, and therefore it is said that metals are having positive temperature coefficient. Metals are having PTC, positive temperature coefficient, and this graph is self-explanatory. See, metal. temperature. As temperature increases along x-axis, say 20 degree, 30, 40, 50, 100, as temperature increases along x-axis for metal, resistance of the metal, resistivity of the metal also increases. And this graph is self-explanatory. But in case of semiconductor, see here, in case of semiconductor at lower temperature, the resistance is higher. At lower temperature, the resistance is higher. And as temperature increases along x-axis, say 20, 30, 40 degree, 80 degree, 100 degree, the resistance goes on decreasing. Therefore, semiconductors are having negative temperature coefficient. Metals are having positive temperature coefficient. So here we also know that, or we know that in reverse bias condition, the diode does not conduct. We know that in reverse bias condition, see here anode of the diode is connected to minus of the battery, cathode of the diode is connected to positive of battery, width of depletion layer will increase. So here in reverse bias condition, the diode does not conduct and it is as good as open switch. It is as good as open switch because perfect open switch not, but as good as, again it is consideration because some leakage current flows. Some leakage current flows. In case of ideal switch, open switch, no current flows at all. But it is considered, this is equivalent diagram. So minus and plus, and this diode is anode and cathode. Resistance between anode and cathode is infinite. And in this way, the IV characteristics in forward bias condition of PN junction diode we have studied both for practical PN junction diode as well as for ideal PN junction diode. In case of ideal PN junction diode, the current should not flow up to 0.7 volt. In case of ideal PN junction diode, the current should not flow up to 0.7 volt, and after 0.7 volt only the current should flow. But in case of practical diode, the current starts flowing before 0.7 volt only. And now one concept in electronics is there which is very simple that we'll try to understand why resistor is called as passive component. So we have completed the IV characteristics, that is forward bias characteristics topic. But now this concept is very simple. So we'll try to understand why resistor is called as passive component. So in electronic lab, when you come, you know that the resistor symbol is like this. The symbol of resistor is like this. And actually resistor looks like this here. There are color bands. There are different color bands. Here it is yellow, then violet, then red. And this band is called your tolerance band. It is a golden. It is a golden. So this looks like this. We know that the symbol of fixed value resistor is like this and its electrical value is fixed. Means when you talk about a very fixed value resistor, 1 kilo ohm, it is a fix. It is not going to change when you purchase it. So its electrical value is fixed. Actually resistor looks like this. Now we'll focus on this. Why resistor is called as passive component? It is very simple, but I am going to explain you. So here, let us consider the resistor of 1 kilo ohm connected to a variable voltage source of 1 volt to 10 volt. So here is the resistor R 1 kilo ohm and we have connected this resistor R 1 kilo ohm to the variable voltage source. It is a variable arrow plus and minus, of course DC voltage source, and this voltage source is changing from what volt? 1 volt to 10 volt. Therefore, no doubt that you see here green color arrows, current will start flowing. This is A means ampere meter. A means ampere meter. You can it is a symbol of current meter. So here, when variable resistor of 1 volt to 10 volt, sorry, variable battery of 1 volt to 10 volt is connected to a fixed value resistor, because this is a symbol of fixed value resistor, only two terminals A and B. So when a fixed value resistor with two terminal A and B is connected to a variable voltage source 1 volt to 10 volt, that is means current will start flowing in this direction, positive to negative, and current meter is here. Now here everything is given. In above diagram, the current will flow from terminal A to B, from terminal A to terminal B for all applied voltages from 1 volt to 10 volt. So for all applied voltages, even though if you apply 0.1 volt, then also the current will flow. 0.2 volt, then also the current will flow because this is a resistor. Because this is a resistor. We have considered here 1 volt to 10 volt, but you can think about below 1 volt also, 0.1, 0.2, 0.4, 0.7, current will flow because this is a resistor, it is not a diode. So in this way, it is very simple. And now what we'll do it here, you read this paragraph. Let us reverse the voltage source. Let us reverse the voltage source. So reverse the voltage source means what? Resistor will connect the same R1 kilo ohm terminal A and terminal B, but voltage source is reverse. Minus is upper side, plus is lower side. Now you are applying the voltage to the resistor in reverse direction. Now you are applying the voltage source to the resistor in reverse direction. So current will flow from positive to negative. Means the direction of current is now reverse. Earlier the direction of current was what here? You see, from positive to negative. From positive to negative, and now the direction of current, because voltage source is reverse, so direction of current is reverse, and no doubt that the resistor is passing the current in now in reverse direction. So here, as shown above, when voltage source is connected in reverse direction to the resistor, at that time the current starts flowing in reverse direction from terminal B to terminal A for all applied voltages from 1 volt to 10 volt, or from 0 volt to 10 volt, for all applied voltages from 1 volt to 10 volt, or from 0 volt to 10 volt. Therefore, resistor passes current in both direction. What is conclusion? The intention to show you this diagram is resistor passes current in both direction. So that is important. Therefore, resistor passes current in both direction. But the value of resistor does not changes for all applied voltages from 1 volt to 10 volt, and it remains as 1 kilo ohm only. So this paragraph is important. We have studied a very simple concept which you studied in 10th standard, 12th standard only. If you connect the resistor to the voltage source like this, positive here and negative here, current will pass through the resistor from A to B. If you reverse the voltage source, current will pass through the resistor from B to A. But remember, when all voltages from 0 to 10 volt applied to the resistor, value of resistor does not changes. Value of resistor does not changes, and here, but the value of resistor does not changes for all applied voltages from 1 volt to 10 volt, and it remains as 1 kilo ohm only. So now let us see here. Resistor is called as passive component because, now here is the main thing. Why resistor is called passive component? Because number one, resistor passes current in both direction. This is the one fact which is very important. Resistor passes current in both direction. It does not take any objection when the battery is changed, means polarity of the batteries are changed. Second important parameter. That is why the resistor is called passive component. Second important parameter is value of resistor does not changes when applied voltage to resistor is changed. Value of resistor does not changes when applied voltage to the resistor is changed, and because of these two reasons, resistor is called passive component. Now let us come to the important part, our why PN junction diode is called as active component. Why PN junction diode is called as active component, and exactly whatever it is happening here, one parameter and second parameter, the same thing is not in PN junction diode. Therefore, PN junction diode is called as active component. So PN junction diode is called as active component because number one, PN junction diode does not passes current in both direction. Junction diode does not passes current in both direction. It does not conducts in reverse direction. It does not conducts in reverse direction. And see here, anode of the diode when you connect to the negative of battery, and cathode of the diode when you connect it to the positive battery, current will not flow. And that is the beauty of PN junction diode. When the battery is reversed, the diode does not conduct, and therefore it is an active component. Therefore, it is active component. Reason number one. Reason number two. PN junction diode is called as active component. Reason number one. Why? Because diode does not passes current in both direction. It does not conduct in reverse direction. Number two. The value of forward resistance of PN junction diode. The value of forward resistance of PN junction diode changes when applied input voltage to PN junction diode is changed. And that is the important factor, because in case of this resistor, you apply any voltage to the resistor. In case of this resistor, you apply any voltage to the resistor, 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 10 volt. Value of resistor R remains 1 kilo ohm only. But in case of our diode, when you forward bias the PN junction diode, Remember, when you forward bias the PN junction diode by connecting anode to the positive of battery, by connecting cathode to the negative of battery, the current starts flowing through the diode after zero point 0.7 volt only. But when this voltage is 1 volt, 2 volt, 3 volt, 4 volt, current goes on increasing. Current goes on increasing, but because of the diode as a semiconductor component, because of the diode as a semiconductor component, the resistance of the diode goes on decreasing. In case of resistor also, see here, in case of resistor, current also goes on increasing. In case of resistor, when you apply 1 volt, there is X current. When you apply 2 volt, there is Y current. Y is greater than X because R is constant, 1 kilo ohm. So applied voltage goes on increasing in resistor, current also increases, but its value does not changes. But its electrical value 1 kilo ohm means 1 kilo ohm only. In case of PN junction diode, in case of PN junction diode, the second parameter is very important. The value of forward resistance of PN junction diode changes when applied input voltage to the PN junction diode is changed. So as applied input voltage increases, the resistance of the PN junction diode decreases. As applied voltage increases, resistance of PN junction diode decreases because PN junction diode is semiconductor component. So here the resistance of PN junction diode decreases when applied input voltage to the PN junction diode is increased because it is a semiconductor component. That is important part. And here this diagram will help you in understanding why PN junction diode is active component. In forward bias condition, yes, it allows the current. In reverse bias condition, it does not allows the current. And when applied voltage in forward bias condition increase, its resistance decrease because it is not a fixed value resistor. It is a semiconductor component. And this is the what beauty of the PN junction diode. Therefore, there are various applications of PN junction diode which we are going to study as a rectifier, one of the application, and so many other applications. So in this way, in today's lecture, we have focused on IV characteristics. IV means current versus voltage characteristics of PN junction diode, both ideal as well as practical, and why PN junction diode is called as active component. And in this way, we'll conclude the lecture. Thank you very much for watching the lecture. You can watch this video again and again and get your concepts clear. And this is the advantage of your online teaching. So at once, if I speak, you can listen it number of times. And in the next lecture, we are going to study the reverse bias characteristics of PN junction diode. Reverse bias characteristics of PN junction diode and some other topic also will cover. Thank you very much.